Hi everyone! This is a project for the manufacturing of fiber-reinforced alpine skis done by Sarah Blust, Matt O'Brien, Anna Marie Pinion, and Sam Stewart for the ME/MSE 4793 course. Ski designs can vary in shape, dimension, and added components based on the needs of the skier. High-end advanced composite skis used by serious athletes rely on the strongest materials such as carbon fibers, while standard engineering composite skis mostly use fiberglass reinforcements. This presentation will focus on standard engineering composite skis because they have a much larger production volume and fewer customization options. For performance considerations, the most important properties for snow skis are resistance to bending, torque, damping, and moisture. For bending strength, a 3-point test is performed. To prevent the skis from snapping during use, the stiffness must be 14 newtons per millimeter under a 300 newton load. The torque strength requirement prevents snapping from occurring during sharp turns, and for that constraint there must be a 19.5 millimeter deflection from a 200 newton torque. Damping is critical for skis to avoid snapping from extended bending and to allow for maximum contact with the snow instead of bouncing off the ground. This constraint states that there must be 16.7 seconds of oscillation after a 20 centimeter bend is released. For moisture resistance, because certain ski materials are hydrophilic, it is necessary to have protective outer coatings in the form of plastic and wax. VDS and ABS plastics are commonly used outside of the wood core and fiber reinforcements to prevent mechanical and chemical damage to the interior. Ski bottoms are regularly waxed in order to reduce friction in snow and enhance movement on the snow. When considering cost, it is important to understand that skis often become outdated before they actually wear out and need to be replaced. Every 5 to 10 years, there are advancements in technology that allow for skis to be thinner, stronger, and more durable. The constraints on the life of a ski has an impact on the total cost and intended durability of each ski. A standard engineering composite set can cost between $300 and $600 depending on the customization and quality. Assuming a set of 180 centimeter skis, this table shows the amount and cost of each material and the total cost of raw materials, which is $98.01. Looking at the material history of skis, original skis were constructed of wood, a feature that is still retained in the core of modern ski designs. Before modern carbon steel tools, more workable woods were preferred like ash in order to ensure easy carving into the desired shape. Around the 1880s, as tool technology progressed, people began experimenting with stronger, harder woods such as hickory, making it possible to build thinner, more flexible skis. The high cost of hardwoods, however, drove the introduction of laminate technology in 1893, where lighter woods such as spruce and basswood were laminated to a base made of the traditional hickory or ash. 2-layer laminates turned into 3-layer laminates in the 1930s, followed by plywood core pressure-bonded aluminum skis, which became popular after 1949. After this time, most skis were laminates, and experimentation with other materials besides wood began, eventually leading to the introduction of polymers and fiber-reinforced polymers in the last 50 years. Wood has remained the core of the ski because it has excellent vibration damping properties and good shape retention. For mid-performance skis, laminated hardwoods are often used. The sidewalls of the skis, where the core meets the edge of the ski, are often constructed out of ABS plastic, with a layer of rubber separating the plastic and the core. ABS plastics are used to improve the torsional stiffness and provide better edge grip, while the rubber is used for shock absorption. Composite layers are above and below the wooden core and strengthen and protect the core. The orientation of the fibers affects the properties of the skis. The base of the ski is made of an ultra-high-density polyethylene called PTEX. PTEX can be either extruded or sintered from powder pellets, and each process affects the wax absorption of the ski. Graphite is often added to reduce the electrostatic friction built up between the ski and the snow. Now we will take a closer look at the composite layer of the ski. For fiberglass skis, there are 2 primary ways in which the fiberglass can be structured in the composite layers. The fiberglass can be wrapped biaxially, meaning the fiber strands are weaved at 90 degrees to each other, or they can be wrapped triaxially, meaning the fiber strands are weaved at 45 degrees, 0 degrees, and negative 45 to each other. Biaxial skis are less stiff and more common in consumer skis, while triaxial weaving produces a stiffer ski and are more common in high-end applications. For the base of the ski, P-Tex can be extruded or sintered from powdered pellets. Extruded bases are more cost-effective but leave little room for wax to be absorbed. This leads the ski to have greater friction. Sintered bases are more expensive but are more durable and porous. The porous nature of sintered bases allows them to easily absorb wax, which makes them faster. Now we will go through the process to manufacture a ski. This flowchart shows the formation of the wooden core. A large log is first put through a computer-operated mill for precise cutting of grooves on the surface and overall shape and thickness of the material. The resulting planks of wood are adhered together to the desired size by interlocking teeth cut into them during processing. In skis with polyurethane cores, the top and base layers are put into an injection mold and the foam is injected with a hose. As it expands and hardens to fill the mold, the foam fuses the wooden layers and becomes the core. This core material is then sanded and cut to create the shape of the ski. Now that the core is made, the layers of the ski must be combined. Before the core material and the rest of the layers are placed into a closed mold, the mold is first coated in a release agent and vacuumed to get rid of any dust. A base layer consisting of graphite-reinforced polyethylene is placed into the mold first. Then, multiple layers of single-layered reinforced fibers are placed in the mold. Next is the core, followed by more fiber reinforcement sheets. An aluminum plate is placed on top for easier attachment of the bindings, which occurs later, followed by more woven glass fiber sheets, and lastly, a silk-screened logo is placed on top. After all layers have been placed, the mold is closed and epoxy is pumped in at around 1000 degrees Celsius, and pressure is applied to minimize air bubbles and combine layers together. The elevated temperature helps the epoxy to flow through the whole mold and impregnate all the glass fiber sheets, combining it with the other layers. After the composite has cured, 3 general steps are applied for the finishing of the ski. First is a sanding belt, which is used to clean off the excess epoxy around the edges of the material and create the ideal shape. The skis then go to grinding wheels to create the angles along their surfaces needed for carving and better control in snow. They then match the skis based on measurements and the 3-point bending test to make sure the skis are close to identical, and then finally the skis are sent to the shops. After production, quality control exists to ensure the buyer knows the characteristics of the skis they are purchasing. The tip radius, thickness, and curvature of the base are measured for each ski to ensure that the ski meets the requirements, and then the most similar skis are paired together. A 3-point bend test is also performed on each ski in order to characterize the ski's flexibility and strength. For some applications, further testing is performed on the product, including friction tests and cyclical tests. To further analyze the cost of manufacturing a ski, relative comparisons between each step of the manufacturing process can be made. The cost of machinery for the closed mold will be the highest initial cost, followed by the cost of the finishing machines. These machines are very expensive, but after manufacturing thousands of skis, the cost per part decreases significantly. The cost of labor, water, electricity, and raw materials, however, are continual costs and become more significant factors when the product is being mass-produced. The pie chart shows the relative cost percentages compared to one another and shows the raw materials have the biggest impact on cost of production, followed by the cost of the closed mold, then the cost of labor, electricity, and water, and lastly, the cost of finishing has the lowest impact on the cost of manufacturing. Thanks for watching! I hope you learned a little bit more about how to manufacture a composite ski.